In this session, we are talking about exponential function. Many people confuse between exponential and exponent. When we are talking about exponent, we are talking about a number that is going to be multiplied by itself, and we know it because the number is written like this: 3 to the second power, and 3 is base, and second is power, and it means that this number has to be multiplied by itself twice. So 3 times 3 is 9, or 3 to the fourth power, and it means 3 has to be multiplied by itself 4 times, right? This is the meaning of exponent. If we have a function, for instance, it says y equals to x to the second power, we know that we have to find the value for x and multiply it to itself and get the value of y. We practice that concept many times. It means y equals to x times x, right? So when we say x to the second power or third power, we mean that we have two sections, two parts. This is our base, that is variable, right? This is variable. And we have a power that is number. Now, what if we have, or we write something like this: y equals to 2 to the x power. In this case, we are not talking about exponent. We are talking about an exponential function. So this is an exponential function. So we have a variable as power, not as base. This is called an exponential function. So exponential function is a mathematical expression in which a variable represents the exponent of an expression. The most fundamental characteristic of exponential function is that we have variable as power of a number. The general form of writing an exponential function is y equals to b to the x power, where the base b is any positive constant and the base b cannot be 1, so it's a number, a real number that is larger than 0 and cannot be 1. The base b could be 1, but remember that 1 to any power is just 1. So in many references, they define it as function that cannot be 1. Let's try some example. Let's solve for x when 4 is equal to 2 to the x power. This problem simply says that we have to multiply x number of 2's in order to get 4. So we know 2 times 2 equals to 4. So we solve for x in this example. Let's say we are asked to solve for y when x is equal to 5. So we have the function as y equals to 1.2 to the x power. So basically it means that we have to multiply 1.2 to the x power, and our power here is 5. So 1.2 times 1.2 times 1.2 times 1.2 times 1, 2, 3, 4, one more, 1.2. it equals to, we can use calculator here and multiply this one, we'll get 2.48832. This is a function and we can easily graph that one. Before graphing it, let's compare exponential function to other kind of function. We have a linear function. We'll learn about it in previous lesson. We have a quadratic function. And now we are talking about an exponential function. In linear function, we basically had y equals to mx plus b, right? In linear function, we have a constant change. Let's say this is our graph. If x changes one unit, the y changes x and y. If this one x changes one unit, the y changes one unit as well. If this one changes 2 units, the y changes 2 units. So you have a constant change. And the graph looks like something similar to this one. Then we have our quadratic function where f of x equals to ax squared plus bx plus c, and this square means that for every changes that brings to this equation, we have the same amount change in the other side. So we'll have a graph that looks like, for instance, this one, or this one, right? Now we have function where the general form is y, or f of x, equals to p to the x power. The graph of this function looks something similar to this one, or you might see it like this one. In exponential function, when there is a rate of change, that change increase or decrease exponentially, and the numbers get large or small very quickly. So let's practice some examples. Let's say we have y equals to 2 to the x power. To graph an exponential function, we go through the same process of finding pairs that we did for linear equation and quadratic equation. It means that we put x values in it to see what the corresponding y values would be, and then we plot the points. So as for this one, let's start with drawing a chart here. This is our x values, and this is our f of x or y values, right? Now let's choose some x values. If x is 1, y is 2. If x is 2, y is, it means 2 to the second power is 4. If x is 3, then 2 to the third power is 8, right? If x is 4, 2 to the fourth power is 2 times 2 times 2 times 2 is 60. Now let's go other way. Let's put 0 into the function. So if we put 0, we know that any number that is raised to the power 0 equals to 1, right? Now let's choose -1, and then our y is half, because based on the property of exponent, any number to a negative raised to a negative number is going to be a reciprocal of the number. So for instance, 2 to the minus 1, we write it as, we bring the 2 into the denominator, 1 over 2, right? Remember that? So then we have, let's choose minus 2, then we'll have 1 over 2 to the second power. It means it's going to be 1/4. What about minus 3? Then we'll have 1 over 2 to the third power is going to be 1 over 8. If we use more negative number for x, we get a smaller and a smaller number as f of x. It never gets 0, but it gets very small in y-axis. Let me remove this section. So if we want to graph this one, we can draw it like this. This is our graph, x-axis, and this is our x-axis and y-axis. So now we can draw our graph. So if x is 1, y is 2, is this point. Let me change my pen here. If x is 1, y is 2. If x is 2, y is 4. If x is 3, y is 8. 1, 2, 3, 4, 5, 6, 7, 8. And so it's going to be here. If x is 4, 1, 2, 3, 4, y is going to be 16. Let's imagine it goes up to here. If x is 0, y is 1. So it's going to be here. Very close to 0, but it's not 0. If x is minus 1, y is going to be half. If x is minus 2, y is going to be 1/4. It can be, I can't draw it very accurate, so let's draw it based on our estimate. So it's going to look something similar to this one. So when the graph looks like this one, it shows growth, like population growth, or for instance cell division, that sometimes is exponential. And this is the general format of exponential function for growth. So this is the first type, type 1, which shows growth and exponential function that indicate growth. Now let's use another example that shows decay or decline of the function, and it starts high above here and comes down to the right side on x-axis. So let's try that one. An example for exponential decay function is y equals to 1/3 to the x power. Basically, in the exponential decay function, you have a base less than 1. We can rewrite this as y equals to 3 to the minus 1 to the x. And we can multiply this one and write y equals to 3 to the minus x. And so the exponent is negative here. Now, let's plot this one and see how the shape of our exponential function decay is going to look like. So let's draw our chart here. We have x values and y values, right? So let us start with a small number like -3. 1/3 to the -3 equals to, in order to get rid of this negative exponent, we can use the inverse of that and write it as 3 to the third power, and that is equal to 27. Then we can choose -2 as x, -2 over 1/3 to the -2 equals to 3 to the second power, and that equals to 9. And let's choose 1 as x, and then we'll have 1/3 to the first power, -1, and then the reverse of that would be 3 to the 1, and it's going to be 3. Then we have 0 as x. We'll have 1/3 to the 0 power, and we know that anything to the 0 power equals to 1. Then we have 2 as x, 1/3 to the second power, and it's going to be 1 over 9. We have 3 as x, then we have 1/3 to the third power, and it's going to be 1 over 27. Now let's plot this exponential decay function. Because the base is a positive number, therefore we know that it's going to be on the upper part of the coordinate. So we can draw our coordinate like this, and this is our x-axis, and this is our y-axis. So we have -1, -2, -3, and 1, 2, 3. Because we have numbers up to 27, we can use the unit 10. So it's 10, 20, and 30. Now, when our x is -3, the y is 27. It's going to be somewhere here. And then when x is -2, y is 9. So it's here. -1, x is -1, and y is 3. So it's something here. Then when x is 0, y is 1. Then when x is 2, y is 1/9. It's going to be here. I guess I forgot to write 1 here, but it doesn't matter. It's 1/3. So we can assume we have a 1/3 here. So if x is 1, y is 1/3. If x is 2, 1 is 1/9. And if x is 3, 1 is 1/27. So we can draw like this. If we wanted to draw the line here, we can see it goes up to let me try it again and see how it goes. It's hard to get it right. So our decay function looks something like this one. As you see, the decline is very fast and very quick. And the decay function can be used in many areas, for instance, in population decline, in production decline, in population decline. So in a decline function, we start from a very large quantity and very quickly the decay happens and it goes down to small number of population. As you can see, the decay function is kind of reverse around the y-axis and is opposite of the growth. We have decline here and we have growth here, as we talk about it in previous example. In both of them, what is important is that the change happens very quickly, and the amount of the quantity that we have increase or decrease very fast. So this is the characteristic of exponential function. So now let's recap what we talk about it in exponential function. So to graph an exponential function, we need to have a table of x values and corresponding y values, right? And then we have the chance to plot the points, and then sketch the graph. Now let's practice. So let's say we have y equals to 3 times 2 to the x power, y equals to 2 to the x power minus 1, y equals to 5.3 to the x power, y equals to 1/2 to the x power, y equals to 3/4 to the x power, and y equals to 9 times 2/5 to the x power. So we are at the end of our session on exponential function.